Yeah, welcome. So the topic we'll be discussing in this lecture is solving problems by searching. So in the last class, we have discussed about different types of agents like reflex agents, goal-based agents, utility-based agents, learning-based agents, all those things. So in this lecture, we'll be focusing on problem-solving agents. Like given a problem, how an agent can solve it. That is, we just gave the problem. We just give the problem, and we expect the agent to provide a solution. Uh, so basically, this type of problem solving methodology comes under a class of algorithms which is called as uninformed algorithms. Uninformed in the sense we don't provide any hint about how to solve, or we don't provide any heuristic in the sense the measure of the correctness of the solution. We don't provide any hint, and also we don't provide any heuristics to measure the correctness of the solution, but we still expect the algorithm to provide the solution. Such algorithms are called as uninformed algorithms. So when you want to design a problem solving agent, first what we should do in the sense, uh, first we have to formulate the goal. What is the goal? So this goal formulation is actually based on the current situation and the performance measure. Current situation can be called as the initial state. So goal formulation basically it depends on the initial state and the performance measure. So the last lecture we have discussed that uh, with the performance measure only we rank the agent, like how good it is doing. And and similarly, problem formulation is the process of deciding what action and states to consider given a goal. So so problem formulation means what are the actions and what are the states uh, to be considered for a given goal state. Okay. So an agent can take different actions, and as a result finally it may take some sequence of actions, and finally it should be able to reach the goal state. A search algorithm is one which takes a problem as input and returns a solution in the form of an action sequence. That is, if you follow these action sequences, you will reach a solution. So a search algorithm is one which takes the problem as input, and it will provide action sequence as the solution. So we started with problem solving, but here we are talking about search algorithm. So most of the problems can be translated to search problems. Okay, if not all the problems, most of the problems can be represented as search problems. So first we have to first, when you see any problem, you have to think like, is it possible to convert this problem to a search problem or not? If it is possible, first you convert to a search problem, and then give some inputs, and then we have many search algorithms are available already in data structures, which will do the job of solving the problem. So that's what here we are talking about. The search algorithm can be used, which will take the a problem as input, and it will provide a sequence. So here problem in the sense, what is the initial state and what is the goal state that it will take as input, and what are the actions that can be performed as the a sequences. Then it will identify what sequence of actions will take the problem from the initial state to the goal state, which is nothing but the solution. So here is an simple algorithm for problem solving agent. It's a very top level algorithm. It's not nothing into specific, but let us see. So the algorithm is simple problem solving agent. It perceives something from the environment and it returns an action. So these are some of the variables. Sequence. Initially this is empty. Why it is empty? Because initially it will be empty because because once the problem is solved only this will be filled up, because once you have the solution, the sequence will have the set of actions set of actions that will move the problem from the initial state to the goal state. So it may, at the end, it may have like A1 to A2 to A3 to A7 to A9 if A9 is the goal state. But initially this will be empty because we don't know how to move from the initial state to the goal state. So state, this describes the current world state. So you can consider this as initial state. And then goal is also initially null. Why goal is null, you may ask? Because here, previously, if you recall, when you solve a problem, what are the things we have to formulate? In the previous slide, we have to formulate the goal, then we have to formulate the problem, then we have to call a search algorithm, which will provide a solution for this problem. So these are the steps. So now this algorithm uh, is going to formulate the goal, and also it is going to formulate the problem, and also it is going to call the search algorithm to solve the problem, right? So everything we are going to formulate here. So initially goal is empty. Problem also, there is nothing is there. Problem, it represents problem formulation, but initially it's nothing. State, current state of the system. So let us assume there is an update state function which will update the current state of the system based on the percept, based on the recent percept, whatever the agent senses. Okay. If sequence is empty, then do this. Yes, initially sequence is empty, we know. Then what it does here, first it formulates the goal. Goal is equal to formulate goal, based on the current state, formulate the goal, what should be the final state. Problem, similarly formulate the problem, formulate problem based on the uh, current state and the goal state. Okay, then call the search algorithm and give this problem as the input. So problem contains everything. It includes the current state and also it includes the goal state. So the search algorithm, what it should do, it should identify uh, the sequence which will move us from the current state to the goal state. So that is what the search algorithm is expected to do. So finally, if the sequence is equal to failure, so either the search algorithm, it may either return success or failure. If it is failure, then return null action. That is, we are unable to solve the problem. Otherwise, suppose if it is returning success and some sequence is there, some sequence is it is giving. Okay, then in that sequence, whatever the first entry is there, that is the goal state. So that will go into action. The first of that sequence will get into action, and the remaining all sequence will get into the sequence part, because if you follow this sequence you will get this action and it returns the action. Okay, so this is a simple problem, simple algorithm for problem solving agent. So basically, mm, it provides step by step. See, here we are it is, we are taking only the first sequence. uh, it is not, we are not taking the full sequence, right? uh, I'm, I'm sorry. So A9 is the goal state. So in this case, first of sequence means it will not return A9. First is this. Okay, it starts with this. So it will return, uh, say this is initial state. So let us not forget initial state also. So because it is starting with initial state. So probably this sequence may include A2, A3, A7 and A9. So first means it will take only A2 and return A2. It returns A2, which means that it is telling to the agent that from A1 you just go to A2. Okay. Then from A2 again, where the agent should go, once again agent should call this algorithm. Once again from A2, the agent should call this algorithm. Okay. Again it will apply all these things. Now it may get, now we cannot say that it will get the same sequence. It may get a different sequence also. Right? It depends. So now it may be a different sequence. It may be A2, A7 or A9. Sorry, A4, A7 and A9. Then it will take the first alone. Then the algorithm suggests the agent to move from A2 to A4. Again, after reaching A4, once again the algorithm Once again, the agent should run this algorithm. Okay. So the how long the agent should keep doing this? The agent should keep doing this until he reaches the goal state. So this is a simple algorithm for problem solving agent. Now let us discuss one. So we'll be discussing this particular problem in detail. For we'll be using this chart or graph for several lectures. So this graph is about Romania too. Okay. So there is a agent in this city Arad. So these are different cities in Romania. There is an agent in the city Arad, and this agent would like to move to the city Bucharest. Okay. And the cost of moving from one city to another city is represented through this graph. So this so all these vertices are the city, and the edge represent either the cost or the time. So it want to move from Arad to Bucharest. So that's the problem. So now we are not going to the solution part. We will be discussing the solution for this problem using several algorithms, but now we are not getting into that. Now we are only focused on defining the initial state, goal state, problem formulation, all these things. Okay. So given this problem, how will you define the initial state and the goal state, all those things? Let us see. So for the given problem, the initial state is nothing but Arad. At Arad, that's the initial state. What's the goal state? Goal state is to reach Bucharest. So reaching Bucharest is the goal state. And what are the actions the agent can do? So there is something called S of X. There is something called S of X. So which is called a successor of the agent. So from Arad, where the agent can move immediately, that can where the agent can move, all those are available in uh, available through the action S of Arad. Okay. So S of Arad will give all these things. So there are multiple options. Uh, the agent can choose anything. So the immediate successor of Arad were Timisora, Sibiu, Zerind. So all these are available in S of Arad, successor of Arad. Okay. Similarly, there are many what you call functions available uh, which the agent can apply. Okay. We'll be discussing. So similarly, there are many actions are available which the agent can apply. We'll be discussing other actions later. Right. Say for example, there is an action available for the agent to check from Timisora. Say for currently the agent is in Arad. Okay, but his ultimate aim is to reach Bucharest. He don't know the full map. First, remember this. He don't know the full map. The agent don't know the full map. He is in Arad, but he can perform some actions. Like if he performs successor of Arad will tell him like what are the adjacent cities. So with this, he knows that Zerind, Sibiu, Timisora are his adjacent city. And also with this, by performing this action, he will understand that these are his adjacent city, and he can reach to each one of these city with this much kilometers. That knowledge he will have after performing after executing this action. Okay, that doesn't mean that he moved here. No, he knows. Then he can choose. Okay, but say now where is Bucharest? In which direction is Bucharest? He don't know still. That's the point. So so from the map, as we see the map, you may say that this is the path or whatever it may be. So uh, but but he can reach Zerind with less distance. So he may be curious to know that is there any way to reach Bucharest from Zerind? Is there a path to Bucharest from Zerind? Like that he may be curious. So he may want to apply a rule. He may want to check is there any way to move from Zerinth to Bucharest or not. Okay, so how, those things and all he can check. For that there is an action. For example, there is an action called result of, he can try this, result of Zerind, comma, Bucharest. Like that he can try. Now, if you see, there is no path from Zerind to Bucharest. There is no direct path. So basically, this action will return 0 or false. It will return false. So now he can understand that, okay, there is no path from Zerind to Bucharest. So he will avoid taking this route. Okay. So like this, there are many actions available. So all those set of actions you have to define when you define the problem. And then the path cost. Path cost is the sum of cost of reaching from the source to destination. There are different. Uh, so so there are also any. I mean, there are also step cost. This is called a step cost. Moving from Arad to Sibia, the cost is 140. That is step cost. Arad to Zerind, the cost is 75. That is step cost. But when you say Arad to Fagares, that is from Arad to Sibia, Sibiu to Fagares, that is path cost. So, so the path cost also should be defined. Okay, and and finally we should provide a solution. A solution is a sequence of actions leading from the initial state to the goal state. Okay. So this is just a problem formulation. So first we need to formulate the problem. Okay, so that's what we are discussing here. So for formulating the problem, all these things are required. We need to define the initial state. What are the actions? What are the goal state? What is the path cost, or any function? In this case, it is a path cost function. Depending on the problem, the cost function may vary. Basically, this is a cost function. Every problem will have a cost function. What is the cost of achieving the goal? Okay, it's not just goal. So previously we have discussed, if you remember, cost. It's not just achieving the goal. It is achieving the goal with least cost or with less money. So uh, or with less time. So this is something like utility. This is a utility, right? Okay. And so only if we have all these things, then only we can work on identifying a solution. A solution is nothing but a sequence of actions that moves the agent from the initial state to the goal state. So selecting, uh, so the real world actually here in this problem of identifying the route from Arad to Bucharest, actually we have abstracted the real world problem. Abstraction means what? Abstraction means leaving the details, or we are not getting into the details. All the details we ignored, and we have taken only the core problem, that is called as abstraction. Because in real world, when a person is moving from Arad to Bucharest, there may be several things he may encounter. We are talking about artificial intelligence, right? So there may be, as a human, there may be several things may be going on around him. The weather may be, what you call, sunny, or it may be rainy, or it may be, or the neighbor passenger may not be cooperative, or or the scenery may be nice, whatever it may be. But all those, we are not getting into all those details. We are only we are only we are representing these problem as a mathematical model for providing a solution. Okay. So that is called as abstraction. Okay, right? So the real world complexities, all those things we are not bringing into the picture. Because if we bring into the picture, uh, uh, then the problem definition will become more complex. So that's what it talks about. So now let us discuss some more example problems, and their what you call, and their initial state, goal state, and path cost, all those things. So if you consider the vacuum cleaner agent problem, so these are the possible states. The whether the room is floor is dirt or not, and what is the robot location. So these are the states. The floor can be either clean or not clean. That is one state. Robot can be either in left room or in right room. That is another state. Actions, the robot can either move to left or right, or it can set. These are the actions. Goal test, there should not be any dirt on any location. What is the path cost? One per action. That is, if it sucks one time, the cost is one. If you consider the 8 puzzle problem, so this is 8 puzzle problem. This is given as the initial state, and this is the goal state. So states are the location of the tiles. There are different combinations may be available. Actions, the tile can be either moved to the left, right, or up or down. Goal test, there is a state, whether we have reached that state or not. What's the cost? One per move. Okay. Now somebody, say for example, you are writing two algorithms. One algorithm is achieving the goal with a cost of 100. That means it has moved 100 tiles. Okay, 100 times it has moved the tiles, because for if you move it one time, then the cost is one. So you have written another program that has achieved the goal state with only 25, with the cost of 25. Now we'll say that this is a rational agent than this one, right? Okay. So it's not just achieving the goal; it's achieving the goal with least cost. So with every problem, we'll associate this cost. Okay. So because with cost only, we can say that how effectively we are achieving the goal. Okay. So this is a NP hot problem. Okay. So it means you cannot solve this in polynomial time. And this is a 8 queen problem. I guess you know what the problem is. So you should place 8 queen on different locations in the chessboard, such a way that none of the queens should attack each other. Okay. So this is actually not a solution, because in this solution these two queens are attacking each other. If you remove this, then there are only 7 queens, right? But there are solutions available. So if you want to formulate this problem, then the states or any arrangement of 8 queens on the board, that is the states. Actions, adding a queen onto an empty square, that's the action. Goal test, 8 queens on board, none attacked, that is the goal test. And path cost one per move, right? How many? I mean, so here the best, the possible solution is achievable with a cost of 8. Minimum the cost 8 is required, right? Because you have to keep 8 queens on the board, right? You cannot achieve anything less than 8, right? So this is a robotic assembling the pots. Robot assembles some pots. Okay. States, coordination of robot, joint angles, pots of object to be assembled. Actions, continuous motion of robot joints. Goal test, whether the part is properly assembled or not. It want to join. Say multiple objects are given, it should join and it should produce a complete object. Path cost, how much time it takes to do that. Maybe you can consider car assembly, right? Different parts of cars were manufactured. Finally, they were joined together, something like that. So these are some of the other problems for which you can try to identify the initial state, uh, goal state, actions, and path cost, all those things. Route finding problems, uh, GPS based system or Google Map based system. Touring, traveling salesman problem, VLSI layout problem, robot navigation problem, automatic assembly sequencing, internet searching, all these things you may try. Okay, fine. So what we are discussing, in the sense, most of the real world problems can be converted to a search problem. Once if it is converted to a search problem, then you can apply any standard search algorithm to solve the problem. Okay. So the basic idea of a search algorithm is given here. So function tree search. So tree search. It takes a problem as a input and it returns a solution. Either it returns a solution or it returns a fail or it returns failure. If there is no solution exists, it will return failure. Initialize the frontier using the initial state of the problem. Okay. So frontier means you can frontier is nothing but a queue. Let us assume frontier is a queue. You know what is a queue? Queue is a first in first out data structure. So the queue initially what it will have in the sense it will have the initial state of the problem. So let us assume initial state is represented as I1. So the queue initially will have only initial state, nothing else. Then continue this loop. If the frontier is empty, then return failure. That is, if the frontier is empty means initial state should be there. But if nothing is there, then it means that there is no initial state. So this is the frontier. The queue is called as the frontier, or we call the queue as frontier. If there is no initial state, then return failure. Otherwise, choose a leaf node and remove it from the frontier. Otherwise, choose a leaf node and remove it from the frontier. Here, leaf node means, let us not get confused. So here, leaf node means we are talking about the solution. We are not talking about the original problem. The original problem may be a complete tree. For example, when you take the Arad Bucharest problem, Arad is here, another city is somewhere here, another city is here, Bucharest is here. Different cities are here. The tree or the graph or whatever it may be, we know the full graph. Then leaf node means we are talking about what? Actually, here we are talking about two different graphs. One is this graph. We are not, this is the problem. This is the actual graph from which we are going to solve the problem. But we are not talking about that. Here tree in the sense we are talking about the solution tree. Okay, we are talking about the solution tree. Choose a leaf node and remove it from the frontier, which means let us assume initially this is the I1 initial state. So whatever this, so let us assume this is A, B, C, D, E. So E is the goal state we want to reach here. So what does it mean in the sense remove A from the frontier? That is I1 nothing but it corresponds to A. So remove that from the frontier and add it to the tree. That's what it means. Choose a leaf node and remove it from the frontier. Why it's a leaf node? Because now, see, initially we don't have any solution tree. Is there any solution tree initially when you start the problem? There is no solution tree because there is no solution at all. Now, this first node you are adding, I1, the initial state corresponds to node A. We are adding that to the solution tree. Now, this is the root node, but this is also the leaf node. Okay, so that's what this means. Choose a leaf node and remove it from the frontier. So this is now removed from the frontier. Now this is not in the frontier. Okay. Next, if the node contains the goal state, then return the corresponding solution. Then check whether this is the goal state or not. No, this is not the goal state. Our goal state is E. This is not the goal state. Then what should we do? Expand the chosen node, adding the resulting nodes to the frontier. Now expand this. Expand A. When you expand A, what will you get? You will get D and B. So expand A, expand the chosen node, adding the resulting nodes to the frontier. So what you get? B, D and B. Add this to the frontier. Now D is added to the frontier and B is added to the frontier. Repeat this. If the frontier is empty, return failure. Frontier is not empty. Choose a leaf node and remove it from the frontier. Which leaf node now? D. D is a leaf node. Now you can see, right? Remove it from the frontier. Okay. If the node contains the goal state, return true. Return the solution. Is it a goal state? No. If this is not the goal state, then expand the chosen node, adding the resultant node to the frontier. So expand. Okay. So when you expand D, what you get? E. Add E to the frontier. That is the queue. Okay. Again go back. Again go back. If the frontier is empty, then return failure. Frontier is not empty. Choose a leaf node and remove it from the frontier. Now, so this is a queue. We always remove the front. So B, remove B. B is here. Is check whether this is the goal. If the node contains the goal state, then return the corresponding solution. This is not the goal. Otherwise, expand the chosen node. When you expand B, what you get? You get C. Add this to the Q. That's what the algorithm says. Okay. Again, go back. If the frontier is empty, return failure. If the frontier is empty, no. Choose the leaf node and remove it from the frontier. Remove it. Okay. Uh, choose the leaf node and remove it from the frontier. If the node contains the goal state, then return that the solution is this is the goal state. Yes, this is our goal state. Now return the solution. Now return this path ADE. Right. So this is how this simple tree search algorithm works. Okay. Fine. Let us stop here for this session. We'll continue further. Thank you.